Okay, so we'll do another example about a distributed load. Okay, so in this example, it looks like this is going to be 5. I'm not going to put units, just distances. 5. Will be L. The one here, distributed load generally is known as W. L. Let's put 12. Okay. Okay, so over here would be again to determine the shear and bending moments diagrams. Okay, so let's say this is our points A and B. Okay, so what is the procedure? Okay, so first thing, three-body diagram. Okay, so I think we talk about these different support conditions. So for these support conditions, how many reactions are we gonna have? 2. We're gonna have one the y direction, one on the x direction. What about the second one? Okay, so let's say it would be dy. Okay, next, what can we do with the load? Okay, at what location? So 1/3 from the right, perfect. So let's say will be here force. Maybe my sketch is not that good. What should be the magnitude of that force? Divided by 2. This is a triangle, no? So this would be 5 times 12, that's 60. Divided by 2, 30. And we said it should be, let's say, at 1/3 from this end. Or if we look from here, eight. Okay, step 2. What do we need to do? Find the reaction. So basically, okay, and remember, conceptually, we need to remove the support so that the internal forces become external forces and we can apply Newton's equation, no? Okay, because Newton's equations are only valid for external forces. Okay, so reaction. So what are the equations we need over here? Let's first do the quickest one. Summation of forces on the x equal to 0. This one will give you what? Ax equal to 0. All right, next equation we can write is summation of forces on the y. This should give you what? Ay plus by minus 30 equal to 0, which is the same as in ay plus by equal to 30. And let's say that's the equation command 1. Okay, next, what can we do? What is the third equation we can take? Okay, about which point you want to take the moments? A, okay, so about A. So remember, you need, every time you take moments, you need to specify about which point. And if you don't specify direction for which is positive, I'm always going to take counterclockwise positive, no? All right. So we do about point A. What is that going to give us? So is the 30 creating a clockwise or counterclockwise moment? Clockwise. So that moment should be what? Positive or negative? So that it would be, so minus 30 times 4. What about dy? So that would be positive. So the force would be dy. What would be the value of the arm? Perfect. This would be equal to 0. So if you do the math, this gives you what? 12 dy equals to 120. So you can solve right away for dy to be equal to 10. Okay, remember that what we do in class, this is, we study together, so you can interrupt me if you have a question, okay? All right. Okay, so now that we know this, what do we do? X substitute into that third equation that we had over here. So we're going to get a y equal to 30 minus by, which means that a y will be equal to 20. Okay, so there's a reason why I do this example. So what should be step 3? What is step 3? Shear and bending moment. So here comes. So here you have the choice. There's 2 different ways to do it, but there's one that is much easier than the other one. So for example, where do you want to choose the origin of the reference frame? Okay, you can do A, but what could you use as well? B. So which one do you think is going to be easier? I mean, when you do a problem, you're going to have to make that choice. I'm not going to be the one making that choice for you. Probably it's easier from B. And if you want, now we can discuss, because let's say I make a cut here. What is the value of this force over here? You see, you will have one rectangular loading plus one triangular, no? Can be done. But what happens if you start from here? You only have a triangular loading, no? So remember, when you solve a problem, you have a decision to make. Some decision might make the problem harder than it is, no? Okay, if you make the right decision, it might be easier. So in this case, we're going to start from B. Okay? You understand why? All right. So let's say here. Okay, I write it here and then I do the figure on the next page, because otherwise I'm going to redo it. So let's select the origin of the reference frame at point B. To simplify the problem. All right. So basically what I'm doing, I'm just going to redo the figure here. A, B, what we have here, we know AX is 0. Let's see what we had here. We had AY equal to how much? 20. UY equal to 10. We know the loading starts from here. Right? This is 5 over here. Okay, and here we're going to select our reference frame to be starting from here. So it will be Y. And this will be X. Okay, so what is the procedure now to find the shear and bending moment diagram? Yes. Oh, so basically you're saying you do this instead of what I've done? Yes, but the problem is that the only reason I do it on the sketch is to specify that it's at point B.
Oh.
If you do it this way, I don't know at which point you're going to put it. Okay, but I mean, but let's say you put this and you put here B, here this way, that's it. Sorry, this is acceptable as well. Okay, either one, I'm fine with it. Right? Okay, so now what is the procedure to find the shear and bending moment diagram? Okay, we need to make a cut so that the internal actions become external. So how many cuts do we need here? Just one. Okay, so let's make that cut and we start from that end. And again, you see it's all the time the same procedure. What do we do now that we made the cut? We made a three-body diagram, no? Let me do a lot of space here. Okay, and you know the cut is somewhere between B and A, not at A or B. Okay, so if I do the figure, what are you gonna have over here? You're gonna have here this. Then we're gonna have here, this goes now reversed, and the general side, we have here B going up. And we're gonna have the moment going that direction. And what else am I missing? We're gonna have here BY. Equal to 10. And remember, this is original reference frame, so it will be X over here. The what? Why everyone? Okay, so I'm missing something here on this figure, but let's see if we figure out what that is. So now, if we want to find the equation for the shear, what should we do? I've done it before. It's a procedure. What is the procedure? In what direction is the shear? On the Y. So we do summation of forces on the Y if you want. So what do we have over here? V plus By. Now, what do we do with that distributed load? You do what? Okay. So you use what? Okay, so what would be the value of the force? Five times X over 2? No, because this is not 5, no? You start from 0. Again, this is supposed to be a review. All right, this is supposed to be known from statics and fluid mechanics. So again, what you need to do is find the equation here of this curve from point B. What would be the equation of that curve? What is the slope of this curve? If you start from here, this will be a linear function, no? Ax plus b, correct? It goes from here. So what is the value of this slope? It's like doing the tangent. Okay, so the equation of this line over here is 5/12 x, correct? So 5/12 will give you the height at any point along the length, no? Since you mentioned 5, what should be the value at the end over here? Should be 5, no? Where what should be the length? 12. So here will be, at this point will be 5, correct? All right. So now, so the value of the force will be what? Obviously, it will be going down, so it will be negative. So what will be the value of the force? What will be, so the force would be the area, no? So what will be the area, let's say, of this element? Height times width divided by 2. So what would be the height? It would be 5/12 over x would be the height. What would be the length? X. And this would be the area of the rectangle, but since we have a triangle, what do we need to do? We take half. Okay. And this, that's it. So this should be equal to 0. So now here we can solve. So we have here V, let's say plus 10 minus 5/24 x squared equals 0. So we're going to get that V, which is in function of x, is going to be equal to 5/24 x squared minus 10. I mean, have you seen that before? Okay, it's normal if you don't use it to forget it, no? Like everything in life, if you don't practice it, you'll forget it, no? Okay, you lose it. All right, so now in order to find the moment, what do we need to do? We need to take the moment about which point? That one never changes. Did that 2 days ago. Always about the cut. Okay, and we specify here again, counterclockwise, positive. So equal to 0. Okay, one quick question before I move, because I want to make sure everything's clear. Is it clear how you find the equation of this line? Okay, all right. So we go here to the cut. So if we look to the cut, what are we going to have? What is the moment created, let's say, by the By? Would that create a clockwise or counterclockwise moment? Counterclockwise. So that means positive, no? What will be the value? So the value of the force is 10. What will be the arm? X, no? B times all that distance x. Now we do the same thing with this one over here. So what is the value of the force? What is the magnitude of the force? First, would this one create a clockwise or counterclockwise? As it is over here. So, okay, so that would be positive or negative. All right. So we go here. What would be the magnitude of the force? What we had before, no? So yeah, but let me just put it here like 1/2 of 5 over 12 x times x. This is the force. And where will that force be applied? So if we say it will be something up like this. So if we do it from this end, what would be this end here? 1/3 of x, no? So what would be the arm? The force is being applied here, speed amount about this point. So what would be the arm? Everything is on the figure. What is the distance between this point and the cut? X over 3 would be the arm, no? Okay, and we have here negative m equal to 0. So basically what we're gonna get here as the equation for the moment, let's say, so we can move this one to the side, so it would be minus 5 over what? So 24 times 3, 72, x cubed oops, I should have put the m, sorry, okay. We have to write one more line, okay, so it will be minus 5, okay, then we have plus and x minus m equal to 0, or we can write down m equal to minus 5 over 72 x cubed plus 10x. Okay, any question? Okay, so be careful because depending on which side you start, you're going to make it more complicated or less complicated, no? Okay. I mean, I'm not planning on doing it, but on the notes I brought, actually they have from both sides. So I'm going to show you the solution from the other side. So it will be on the recording if you want to look at it. Okay, so from these notes I brought, basically, I think we discussed about this equation last times. Again, this should be derived in solid mechanics, but when you have a distributed load, you can have that there's a relation distributed load is equal to dV dm, okay? And the other relation is that the shear force is equal to dm dx. Remember, we did this one, and we said what would be the moment maximum? How do you find the maximum of the moment? M. You take the derivative with respect to x, and you equate that to 0, no? And you say you can find the location. So actually, the location of the maximum bending moment corresponds to the location of what shear? Where the shear is 0, no? And we use that condition. Remember the first example, okay? So again, the important thing is those two equations. That's all that's important here. So in this case, if we start from end A, basically this is the steps again from 0. Looks like I started from 0. So obviously, you're going to get the same values for the reactions. But now we start from this end. All right? So end A. now from point B. So we follow the procedure, we do the so yeah, okay. So basically here I show how to find the equation. So from this end, what should be the equation? What should be the equation at x equals 0 should be equal to what? 5, no? Okay. What should it be at the end at 12? 0, no? So you multiply this by 12, that gives you what? Minus 5 plus 5 will be equal to 0. Otherwise, you can find the equation of the line, but just assuming that it's of the form, whatever, y equal ax plus b. Actually, I think I put, when I look at the notation, would be m. So assume y equal mx plus n. So you see, you need 2 points in order to define the equation of a line, no? At x equals 0, so this is 0, 0, this is equal to 5, you can find m. Yeah? If x equal 12, what do you know? Y is equal to 0, no? You substitute, you find the other value. So the equation of the curve is y equal minus 5 over 12x plus 5. So now the prime, when you do the free body diagram from the end A, you see it's a lot more complicated. Because when you start from this end and you make the cut, what do you have? You're gonna have one load which is rectangular over here, and one load that is like triangular. Yeah, okay. But after that, basically we do the same procedure. So if you do the equation for the shear, what would be the equation of the shears? Would be minus V plus the value of the reaction. But now you need to be careful. What would be the value of this? So we look at the first one, will be minus X, and what would be the height? Is this part of the equation here, no? Yeah. And now for the load 2, what would be the height? Will be basically, this would be the height of this, but now this height of here would be all that distance minus this one, no? That's what I have here. So the area would be x over 2, because it's a triangle of the change in height. So you see, this becomes a lot more complicated, no? To start from that end, okay? And if you want, I'll show you. So you do the algebra, and from that end, that is what you get, the equation. And okay, looks like I also show a different way to do it, but forget about that one. Let's go to the moment equation. All that stuff would be, oh. So for the moment equation, you can do the same thing. Probably it's easier to integrate. Yeah, okay, so a moment equation, you do the same. Okay, but once again, here the goal is not that you make it the complicated way, is that you pay attention and select the easiest way to do the problem, no? Okay? Okay. So this will be it for this part of shear bending moment diagrams. Now I'm going to do another review about bending stresses. All right, so I remember the title of the first one. So review. Stresses in bends. Okay, so I'm going to go really to the basic stuff, okay? So what are the 3 types of stresses that you are familiar with? You can have what? Axial stresses. What are axial stresses? About which axis? About the one that goes through on the axial direction of the surface. Yes? So what will be that one? Okay, you want longitudinal, but I want you to think more about the one that is, if you want, perpendicular to the cross-section area, no? Yeah? Because what about if I do the figure this way? Then it would not be longitudinal anymore. Yeah, I mean, longitudinal would be good along the length of the element. I would take that. Okay, this may be something, this could be called, since we're talking about this, maybe it might be easier to call this one normal stresses, because it will be normal to the surface, no? Since we're looking about notation. Okay, what would be the other option for the stresses? Correct, so this time, but we do the same figure. What would be the other option is to have the shear going in that direction. Usually you use the letter tau, no? For the shear. But basically, this one is called, let's see, shear stresses, or what could be another name? Tangent, because it would be tangent to the cross section. Okay, so what does that mean? That when you solve structural problems, you can have either axial stresses or you can have shear stresses, no? Yeah. Let's say if you have a stress which is at this angle, it will have one component of axial stress and one component of shear stress. Yes, normal tangential. So we can break all the stress about this one. So now, what happened in bending? So what happens when a beam is in bending? So for instance, we can take any beam, okay, the ones we, if you want the ones we have done before, it doesn't matter. Okay, just put one force right here, doesn't matter, do it very simple. Okay, P. So what is that force going to produce? That's what we have just done. That force is going to produce what? What is it going to produce? Shear V. And bending moment, M. Okay? So what is the bending moment going to do? That one is going to induce what? Axial stress or normal stress? Axial stress or shear stress? Normal stress or tangent stress? But look, you have 50-50. I mean, when you what's going to happen if you do something that is this long here and you bend it? What are you doing to the cross section? The top will try to become shorter and the outside become longer, no? So what does that mean? It will be actually in action, no? One side will be in compression, the side will be in tension. Maybe something I should have done that before, but basically induces axial, if you want, normal stresses. Okay, so I'm just going to do the basic stuff here, the basic concept, then I will give more complicated equations. All right, so what is the expression that you have here for that stress? Let's say this is y and x, okay? If you want. X, y, and this will be then D, okay? Okay, the bending, since will be on the axial direction, will be in what direction? X, no? Okay, now, the moment is about which axis? The axis, so maybe you remember this equation, but if you want to start putting more detail, mz, then what is that equation? Did anyone remember? Is m, in this case, y over I. So basically, let's say the cross section of this beam is this one, okay? It's simply rectangular, okay? I'll put it here. So if I look here at the cross section of the beam, this beam will be oriented in what direction? So it will be, let's say, so this will be y and whatever, z, no? I put in the middle, but you have to put in the middle, okay? So now, see, go understanding. The important thing is to understand the equation. So what is y? Y is the distance from where? What was the name of this line over here? I'll help you. Okay. The neutral axis, no? Neutral axis in most of the cases correspond to the CG, no? Okay. The one here is, so Y, distance from neutral axis. Okay, mz is bending moment about the axis. Here we have an I. What is I? Okay. So it's area moment of inertia, but if you want, you can just call it moment of inertia. Okay, so what is the physical meaning of the moment of inertia? Okay, so it's related to the cross section. Yeah, perfect. Resistance to what? You're on the right direction. Resistance to move, but in what direction? To deform in resistance to bending, no? Okay, so what happened here? What happened? You see, this is the stress due to bending, no? So the higher this one here, the less this is going to bend, no? Yes? Okay, all right. So moment of inertia. Now, you agree that this, I mean, it's triangular here. This can bend in what direction? It can bend about this axis. You want this way. We should bend about this axis, no? And then it would bend this way, no? So in this case, this is bending about which axis? Bending about the Y or the Z? or the X. Sorry. Okay, so it's bending about the Z-axis, no? Okay, but I'll give you the three choices. So if we want to be detailed, this could be about I sub Z. Okay, and here I'm not going to put a sign here. Okay, then what else? Since we were discussing this stuff, so this is going to bend in this direction. No, the beam is bending down. All right. So if you want, this will be the top of the beam. Let me do it this way. So this is the top of the beam. It will be the bottom. Okay, if it's bending this way, this side of the beam will be what? Tension or compression? First, what is tension? Tension is defined as what? Perfect. And how do you define compression? You push it together, okay? Okay, so now that you know this. And Jali, what is the sign convention that we use? Positive for tension, negative for compression, no? Yes? Correct? Okay. So if I look at this beam, what type of stress do you have? Tension or compression here? Let's say at the top of the beam. This side will be in compression, and this side here will be in tension. Okay, so here comes the stuff. You see, I didn't put a sign over here. But if I ask you what is the stress, let's say at this point over here, on top, let's say it's 500, okay? What should be your result? You either put equal to negative 500. I mean, there's three options if you want, but if you put negative 500, I do understand that you are saying that that stress is in compression, no? Okay. Another option would be that you put 500 and then you write down on the side compression. Okay. Or you put minus 500 and compression. Okay. But you need to tell me. You see, I don't put the sign over here, no? I want you to do it with the understanding. Okay. On the other way, if we look at the stress at one point here, that one should be what? Positive or negative? Positive. And you need to let me know that I will understand is intention. Okay, so all right, one more thing we need to do over here. Again, we studied this simple case over here. Now, the shear force if we follow the same notation, okay, I think that makes sense, induces what? Shear stress. Shear stress, no? Okay, so basically we look at the cross section. Yeah, why? If I do it normally, I should do it up, but it's fine. It doesn't matter, do it up and down, okay? That's not that important. Doesn't matter. This is not that important. So what's important over here is that I'm not going to go that much detail in email, but this will produce what? A shear. Anyone remember the equation? dq over it, where T is the thickness of the beam, V is the shear force, Q is the first area moment of inertia. I will go in more details when we go here, okay? And I, okay, in this case, should be about which axis? I mean, same as before, this should be, oh, I didn't put it here. So this should be here about the Z, but the Z over here for the previous equation. And this one again, this should be Z. Okay, IZ is the moment of inertia. And T is the thickness. Okay, I will go back into detail on this, okay, later on. Now, I want to concentrate more on just on the bending, okay? Okay, before I move maybe to the next bending part. Why am I more interested in bending than shear? Just because I like it. Go ahead. Okay, you're on the right direction, but basically what you're saying is correct, okay? But that means, so what should be, how should be the structure like for that to happen? What is an assumption that you have been doing maybe without knowing it? You're on the right direction. So what needs to happen for something to bend before, if you want to have it in shear, what needs to happen to that structure? Okay, so let me try to give you a hint. So if you have something long, okay, long bar, how are you going to try to break it? Bend it, correct? Now, what happens if your bar is this short? Not very much. So how are you going to try to break it? Probably you're going to try to twist it. No, that twist now is shear. So what is the assumption that generally you are doing, that you have been doing, is that the structure is thin and long, or a slender member, no? So all the equations you have derived so far for stresses and bending, you have been making the assumption is a long, slender structural members, okay? Or they are much longer than the width. Does that make sense? Okay, so that's why I'm more interested about the bending, because if we make that assumption, the structure is probably going to fail before what? In bending or shear? In bending, okay? That's why we pay a lot more attention to bending than shear. If the structure was short, now what would be the way to break it? Would be shear, no? Think about your head, you know? How would you break the structure? If you're going to break it in bending, probably bending is critical. If you're going to break it in shear, probably shear is critical, no? When you're going to break it, all right? So again, I will go back to this equation to a lot more detail, okay? Basically, when we need to, for example, design bolted connections, or if you put like rivets or whatever, this becomes important, okay? But not for this, because the rivets or the bolts will break in what? In shear. So for these cases, this will be the important part, no? Okay? But for now, it just say beams, okay? So next, so let us consider the more general case. So in this time, we're gonna have, I don't really know how to plot this too well, but let's try. Okay, so in order to simplify, I'm going to make this clamp, okay, or cantilever. It's just for to show the forces. So in this case, what we're going to have is a force on the x. So let's say it would be the x-axis. I think that's what we used before. Yeah, x-axis. This could be now the y-axis. So I'm going to put here also a force on the y direction. And I'm going to put another force, so x, y. So the z should be coming in that direction. And let's say I'm going to put here force on the z. Okay, so now this became a little bit more involved, no? So now this structure, what can happen to this structure? If, let's say, let's just look at one force at a time, okay? Fx, this is going to induce what? A normal stress on the x direction, no? What would be the value of that normal stress? Would be f of x divided by a, no? Yeah. Now, so we took care of this one. Now, what happens if we only apply f of y? This is going to produce what? Okay, it's going to produce shear, but what else? This is producing a bending moment about this end, no? So this is going to bend up and down. So this is going to produce what? It's going to produce axial stress due to the bending about which axis? About the, yeah, about z or x, okay? It will bend this way, okay? Let's just, we pay attention now to the z, okay? About this one, no? Now, what happened about the Fz force? So Fy will make it move up and down. This one will make it move what? Back and forth about the y-axis, no? And this will also produce shear, but here we're just talking about the bending stresses, no? But this will also produce a bending moment about the y-axis, no? Okay, so let's say I give you this problem. So what do you need to do? You need to solve. So after the body diagram and solving for reactions, and it will be the same thing. So let's say you must, I mean, not you must, you should. Solve for shear and bending moment equation in the following two planes. So basically, why I'm talking about two planes, because you're going to have bending about which plane? About the XY plane, no? Moving up and down. So you have, if you look at XY plane, This time we're looking at the bending up and down, no? So in XY plane, solve, if you want, for, okay, if you want Fy/Vy, that would be the shear force in that direction. That would be related to that. And the moment about which axis? Which one is making go up and down? Okay, about the Z, no? If you move about the Z here, this way, no? This is gonna bend up and down, no? Yeah? I mean, do you understand here what I put Vy or Vy? Because the Vy will come from the Fy, no? Okay, let's put here Vy. I don't want to confuse, put Vy. So now we look at the motion in this one. Next one, we need to look at the motion in this plane. So what is this plane? No, if we move this one, we always have the length. Now it's moving about the, so we look at the XZ plane. You solve for DZ and the moment about which axis? Which one is the moment that's going to make it move in and out? And M1. Okay, let's see if I can put everything here. So if we look at the cross section, maybe I'm going to do it here. So this is this cross section over here, okay? So what would you have over here? This would be the what? Y. And what should be the one over here? Z. Again, so this is the neutral axis if you want. But if you look at it, I don't have that many colors, but the bending about this one will be what? This would be I sub Z. And this will be I sub Y. So I sub Z would be the bending up and down. Okay, resistance to the bending in the up and down will be the Y. Resistance back and forth will be about the, sorry, other way around. No, it's correct. Will be the Y. Yes? One of them is resistant to this type of bending, the one resistant to this type of bending. Okay? But again, we say that all the two types of stresses we can have are axial stresses and shear stresses, no? So all these bending moments induce what type of stress? Shear or axial? We just did it. Axial. So would be sigma x. So what would be the value of the force of F? What would be the axial stress produced by the force F of x? This one is easy, it's force per cross-sectional area, no? Okay. Now the next one is we're gonna have a stress, axial stress produced, let's say, by the MZ, which is the one that make it go up and down. So it will be what? MZ times what? Y going up, no? Yeah, up or down. This is bending up or down, so we do the Y. Divided by what? This is bending about which axis? I see. And then we're going to have another axial stress due to the bending in which direction? This one, no? Yeah, sideways if you want. Up and down and sideways, no? This one. Okay? So it'll be the moment Y which is bending about which axis? Y, no? Would be resistant. But I think you're right, okay? Or not. What should be now the distance? We are looking at so before when it's going up and down, we look at the distance top to bottom, no? From the neutral axis. If you move at this direction, you're looking at what? Left or right, so that should be Z, okay? So it should be Z. So now, in books, you're going to find probably that this equation is equal to this. So if you want, you can leave it that way, but I don't like to put it that way because how are you going to decide if this one is positive? I mean, if this one is positive, how are you going to decide this one is positive or negative? By understanding, by isolating that load and figure out if it's tension or compression, no? Yes? How are you going to figure out the sign of this one? By figuring out if where you are the location is tension or compression. And this one, the same thing, no? So even though in books, generally they will give you this because it's what the moment will induce, I'd rather just put positive on everything and that you get the sign from understanding. Yes? Okay? So what over here is the note. Get sign for each term by looking if it is in tension, that will be positive. Or compression, that will be negative, no? Okay, so there's no one answer because, for example, let's say in this case, okay, let's look at this case. Let's say we look at whatever, which point you want. Let's say we look at this corner, okay? Here, this corner over here. This point over here. So this point will be what? If we look at the FX, we always give the load in what? Positive or negative? This will always be in tension, no? So this term, the way it's plotted, will be positive. Now, what will be the moment created about the Z? This point over here will move up. So if you look at this point, it should be what? The second term should be what? Positive or negative? This is moving up. No, because this part will be the inside part. If you want the smile, this will be the outside, no? Yes? So if you look at it, really this point, the way it's plotted, this point will be, let's say this point over here, no? Yeah? When it's moving up, then this one will be positive, this one will be negative. Yes? Yes? Okay, what about this point over here? Now, what happens when it moves this way? Yeah, but it will be tension or compression. Again, it will be on the short side, it will also be in compression. So in this case, if you look at this point, this term will be positive, negative, negative. So that's why I don't like to give one equation and you take it as a recipe. Oh, I got an answer, but I have no idea. I want you to break one term at a time and understand what's happening in the structure, no? Okay. So we have class until 11. All right, so maybe I have time to start anything else. So let's maybe look at the assignment that you have and see if I can give you some things. All right, so ME304 assignment. So let's see what I gave you. Okay, so from here, what is the best side to start from? Right or left? Probably right, no? And again, so I've been nice over here. Yeah, I've been nice. Anyway, so this will be the first. I mean, I don't remember I give you this, but I give you this. So first assignment. Second assignment, what can you expect? Loads in every single direction, no? So basically here, you only need to solve the shear and bending moment diagram in one plane, correct? Because it's only forces in one plane. Second assignment, something similar. So if there is loads like the one we just did in class on the X and Y over here, you need to redo the whole procedure for two different planes, no? So it might take a while, no? Yeah, but I mean, it's good to start with this one. Okay, I'm not complaining. So basically, why did that go to the middle? Okay, I don't know why this happened. But basically, I just follow the steps here. I ask you to do the steps. So draw a free-body diagram, determine reaction, find shear and bending moment equation, plot them, whatever you want. I didn't specify MATLAB or whatever you want to use, no? You plot them, no? Determine the deflection curves, and knowing the maximum deformation cannot exceed 0.02. Here, what I'm asking you to do is what? So basically knowing that the deformation cannot exceed this, and under stress cannot exceed this, you're gonna have to, you can solve for each one of these two for I, no? Okay, and then I think I plotted here. What I want you to do here is to go what? Which I do you need to use? The I of X or the X of Y? Let's see what is the figure. Good question. There's no figure about the cross section. I'm guessing this is what we call for us the Z. Yeah, and this will be, so it will be the bending up and down. This will be the bending side to side, no? So this is up and down, no? So you solve for the X, sorry, for the two equations, from the one from the deformation, you solve for the I, the one from the stress, you solve for the I, no? So which one should you take? Basically, I'm not going to give you the answer, the one that is controlling the answer, no? So you can get one value, and you will come here to this section, and you might have more than one choice, but you can look here for the I you found that the Y flange that you need to buy will be whatever, 610 times 55 or whatever is this number. Yes? Any question about what needs to be done? No? Okay, since we have 4 minutes. Maybe I can put it here on the back of this one. Okay, so what do you want me to repeat over here? Okay, so let's look at this point, okay? All right, let's look at this point over here, the same as before. So if we just look at the force F of X, you agree that this is just going to create tension, no? So tension for F of X. Now, F of Y is going to produce the moment about the Z, no? F of Y is going to produce the moment about Z.
Okay, all right. So it's like the right-hand rule?
No, it's understanding. Fy is going to create mz. Now, if this is create mz, how is this going to bend? Upward, no? Okay, so this side of the beam will be what? Okay, so that's in compression, and that point here will be in compression because at the top. So I was asking you this one, it will be tension, no? Because it's this one up. You understand? Okay, if you want, since we are doing this, the next force is what? Is Fz. Fz is producing a moment about which axis? Y, no? About Y. Now, how this will bend? If we have to look, I cannot do sideways, but if this was the plane, let's say this will bend on the positive Z, no? Yeah, so it will be, this is not Y anymore, this is Z, no? This is ZX, okay? This is YX. Just try to plot into this. So this will plot, let's see, this will come away from the Z. So again, the top will be in compression, no? So it will be negative. Yes?
The problem we're solving for the inertia, what moment do we do?
Okay, that's in the problem you're having is just one like this. Okay, so basically you have here, you only have what, X and Y. So all these forces over here will be produced in a moment about which axis? Z. Okay, but be careful because when you go to the tables, I think what they used on the tables, they use this, okay?
What moment and what point of the beam? So I think
The beam is uniform. You assume the beam is uniform. Uniform cross-section throughout the whole length of the beam. Okay? I mean, I think your question is, which point do you choose for the moment? You need to choose the point of maximum moment. So when you have the equation, mzy over iz, what is the m you need to take? The maximum value of the moment, no? The critical point. Yes? All right, so start working on the assignment.